One important property for DC motors. When the brushed DC motor or the brushless DC motor rotates, each winding generates a voltage known as the back EMF or the back electromotive force. This voltage opposes the main voltage supplied. You can find more information about this back EMF by visiting Lenz's law. So remember that the back EMF polarity is always in the opposite direction of the energized voltage. In this case, our energized voltage is the supplied voltage at the brushes. Please remember that the back EMF depends not only on the angular velocity of the rotor coils or the RPM, but also depends on the stator magnets and the magnetic field it's creating within the rotor coils, and also it depends on the number of turns of the actual rotor coils. Therefore, for a constant magnetic field, which is the case of the stator magnets here, then the back EMF will be proportional to the angular velocity of rotation only. In order to find the back EMF voltage relation with the angular velocity, we know that the angular velocity of the motor is directly related to the input voltage by a linear relation where the slope is equal to the voltage constant. So we can write the angular velocity equals to kV V. This implies that the voltage is equal to 1 over kV times omega. Now 1 over kV is the K, what we call the Ke, which is the back EMF constant. So we can express the back EMF as Ke omega. Now remember, this voltage is always in the opposite polarity to the applied voltage. Please be also aware that the torque produced by the DC motor is linearly related with the input current. So if the x-axis is the current and the y-axis is the torque, then the linear relation is governed by a straight line with the slope of Kt. Kt is what we call the torque constant. So the torque can be expressed as T equal to Kt multiplied by the input current. So let us apply the fundamental physical laws in order to derive the mathematical equations that adequately describe the electromechanical actuator we have here. Generally speaking, dynamic systems are presented by differential equations. For this DC motor, we can start from the applied voltage. We can consider the electric circuit as such. So we have a voltage input. We can assume that the windings have a resistor R, a total of resistance R, and an equivalent inductance L. Now R and L represent the actual rotor coil within the motor. Now remember, we said before that there is a back EMF voltage which is a function of the angular velocity. So we can present this as a voltage source as well. However, since the back EMF is in opposite polarity to the applied voltage, then we're going to express it as minus plus, which is opposite to the applied V. So this is the electrical representation of the DC motor. And now we shall look at the mechanical part. So if we consider that the rotor coil and the commutator, including brushes and shaft, can be simplified as perhaps a shaft with a mass that has a inertia J upon rotation. And if we consider that the electric circuit applies the input torque as T, then this obviously will cause a motion in the direction of the applied torque as theta. The friction can be presented as a function of the damping coefficient B and the angular velocity, or theta over dot. Now remember, this B is the viscous damping coefficient which we used in the past to express the heat generated in shock absorbers. If you recall, if you consider a shock absorber, for example, we used to express that the heat generated or the friction as B, which is a viscous damping coefficient, and multiplied by the velocity, or B x over dot. The same thing here, this is B, the damping coefficient, and theta over dot is omega. Now if this motor is to be connected to an external load, then we will have another torque opposite to the input torque. We can denote this as TL to represent the load. So the electrical part can be modeled using Kirchhoff's voltage law, and the mechanical part can be modeled using the Newton's second law. Oh, that's the back EMF voltage. I forgot to put this down. Before applying the laws of physics to find the relation between the input, which is the voltage, and the output, which is the theta, it's important to go over some of the assumptions. We are assuming that the DC motor is 1. Linear. Even though we discussed before that the angular velocity is a linear relation with the input voltage, this is not true over some voltage ranges. For example, at high voltages, this may not be the case. For example, if you apply, let's say, 5 volt to the DC motor, and let's say you have 100 RPM, when you apply 10 volts, you may get 200 RPM. However, if you applied, say, 20 volts, this may no longer be the case, so the output could be 150 RPM. So we are assuming that we are operating the DC motor along its linear range. The second assumption is that the DC motor is time invariant. We are assuming this, even though in reality this is not the case. We know that the brushes are in continuous friction with the commutator. The viscous damping may be also changing with time due to maybe heat generation and so on. So this is not accurate, but it's a good assumption so far. As far as the mechanical part is concerned, we also assuming that the shaft is rigid, right? And there are no torsional effects, no torsional spring effects, or any rotational damping associated with it. And the fifth assumption is that the shaft has no mass. So this shaft here has no mass, and we have simulated the mechanical part as a one lump mass with a inertia of J. Now we can work out the electrical relationship using Kirchhoff's law and the mechanical relation using the second Newton's law. Now applying the Kirchhoff's law this way, what we get is voltage N minus the resistor multiplied by the current in the rotor coils minus the inductance voltage minus the friction voltage, or what we call the back EMF. And this is equals to 0. Now the mechanical part, following the second Newton's law, can be written as the input torque. We subtract the friction. We also subtract the load. This is going to be equal to the inertia multiplied by the angular acceleration. So this is the electrical part, and this is the mechanical part. Now remember that our input is the voltage supply and the output is the theta. Also remember that the back EMF was previously calculated as equals to Ke theta over dot. Also remember that the torque is equal to the torque constant multiplied by the current. So the two equations can be written as also the mechanical part can be written as torque constant I minus P theta over dot minus TL equals to J theta 2 dots. Also remember that in SI unit the torque constant is equal to the back EMF constant equals to 1 over kV, and this is only true in SI units. For this reason, we can call all of them as K, and we can remove the KE, leave it as K. Also we can remove the T from there and leave it as K. This will simplify the calculations. By this, we've come up with two equations, and the next step is perhaps to find a common variable, and we can substitute one equation into another. This will be much easier if we apply the Laplace first, and then we look at the common variable. In this case, the substitution will be much easier. So let's start with the last two equations we arrived at to sort out the mess. Let's create some space. This is the mechanical equation. Oops. Okay, so applying Laplace to both equations, we get the first one is your voltage supply. This is the input voltage. Now I is my variable, so that becomes in the Laplace domain as well. And the derivative becomes minus L S I of S minus, also the theta over dot is like d omega over dt. That means it's k times s theta s equal to 0. So this is one equation. The second one is similar, so that's going to be k I s minus damping coefficient. Again, theta over dot is s theta of s minus t load. Now if we consider at the moment that TL is 0, because as far as the project we are doing, we will not be adding any loads on the DC motor, so it's fair to say TL equal to 0 for now, equals to J S squared theta S. If you notice here that the input is V in S and my desired output is theta in S, so this leads to the conclusion that it's easier if I find I of S in one equation and substitute it in the other. This will give us a relation only between the input voltage and the output angular position. So this is equals to S into J S plus B theta of S. This can be further simplified as I of S equals S theta in S JS plus B over K. Now going back to the electrical equation and taking I of S as a common factor, we have Vs minus Ks theta in S equal to I of S into R plus Ls. Now we have to substitute this one in here. And since we are interested in the output angular velocity, then perhaps we could use the S theta of S as theta over dot ns. The same thing in the mechanical equation, we can consider as theta of s as theta over dot ns. So making these substitutions, I get v ns minus k theta ns equals to, now replace the I of s here, it's equal to theta ns js plus b over k multiplied by the r plus ls. Now moving this term to the right hand side and taking theta of s as a common factor, we have vns equals ls plus r into js plus b over k plus k multiplied by theta over dot ns. Now remember, this is the input, which is the voltage, and this is the output we are interested in, which is the angular velocity that we're trying to control for that DC motor. To write this transfer function, it has to be output over, I'll just write it somewhere there. We have to write it as output over input equal to theta over dot ns over vs. This equals to, if you do the calculation, you will get something like k over js plus b multiplied by ls plus r plus k squared. And the k squared is coming from the common denominator over here. So try this out and compare it with question number 7 in your project. Question number 7 was to obtain and derive the mathematical model of the supplied DC motor. Check this up and I hope you get the same results. Note that B sometimes is referred to as the friction constant Kf. They are the same. Also remember that Ke is the same as Kt when we are dealing with SI units, equal to K.